right, we've looked at the discrete time, linear time invariant Lyapunov stability. Now we're going to look at the continuous time, linear time invariant Lyapunov stability. So in this case, we start off with this differential equation, x dot is equal to ax. Here's our candidate Lyapunov function. We take the derivative of this along the system trajectory. So I can use the chain rule or I can use the product rule. The product rule says x dot px plus, x transpose dot px plus x transpose p x dot. So I differentiate this one and then I differentiate that one. So that's the product rule in a matrix case. And x dot then is equal to ax. Okay, so transposing this, I get x transpose a transpose. Both of these two terms have x transposed on the left, x on the right. I can factor out x transpose on the left, x on the right, and I get this expression. I set this equal to minus x transposed qx, which gives q is equal to minus this quantity. So kind of like what I've done before. And so now we have, here's our Lyapunov function, candidate function. Here's our derivative along the system trajectory. They satisfy this Lyapunov equation. So this is a continuous time Lyapunov equation. We've already looked at the discrete time Lyapunov equation. This is a Lyapunov function, that is, V is a Lyapunov function, if P is positive definite and Q is positive definite. So once again, we have a linear matrix equality, and we can also look at this stability problem in terms of the linear matrix inequalities, like we did. So again, these inequalities are in a sign definite sense, that is positive definite. So this quantity is a negative definite matrix. This is a positive definite matrix. As in the discrete time problem, I can also obtain a closed form solution for the for P. If my system is stable, then e to the at goes to 0 as time goes to infinity, and therefore this integral converges, and we can actually define P this way. And so in the proofs video, you'll be able to see how this comes about. So again, it looks really complicated. First time you see it, it looks really complicated and it looks really nasty, but it's actually not that bad. And in fact, this will actually serve to save us a huge amount of time for certain problems. So anyway, as strange as that might seem, it just means that the problems are not that simple. Okay, so it turns out that when you have a Lyapunov solution, it's unique. So to show that, we basically suppose that there exist solutions P and P1. So they both solve the Lyapunov equation for a given Q and for a given A. Okay, so suppose there exist equations, solutions to the equation. Turns out these equations don't always, even though they're linear in P and Q, they don't always have a solution. It actually depends on whether something about A. In particular, if A is stable, it will always have a solution. Okay, and so for any Q, this will always have a solution in P for any Q. But it turns out that if your A matrix has eigenvalues on the imaginary axis, you will not actually get, there will be no P that will satisfy these equations, which is kind of weird. But this says, suppose there exists a P and the P1, both of them satisfy this equation. I can go through and show that P must be equal to P1, or rather P1 must be equal to P. That is, there's really only one solution to this equation. And so this is proved in the proofs video. All right, exponential rate of decay. So suppose we have this differential equation. So we've kind of looked at this already. V dot less than or equal to minus alpha V. This is associated with the solution V of x of t is less than or equal to e to the minus t, V x of 0. And in fact, we can get a bound on what this quantity must be. A bound on this based on this inequality. So in other words, we have some alpha here. So where do I find that alpha? Well, one way to find it is this way. In general, we can do this. V dot of x is equal to minus x z transpose. So I just put z in here as a placeholder. Minus z transpose qz this quantity in terms of the function z is less than or equal to the smallest singular value of q times the norm of z. Okay, we can go through and actually prove this inequality based on this. So here I say lambda min, it also is the smallest singular value. The singular values are the eigenvalues for a positive definite matrix. And because q and p are related by the Lyapunov function, I can actually go through and show this. That this this quantity here is less than this quantity here. Okay, so and this is associated with the largest singular value of p. So I have these inequalities, and these inequalities are solved are true for any p and any q. I might be able to actually, so I get this value alpha. This is a value of alpha that satisfies this relationship for this problem. It's possible to find another alpha, a larger alpha than this, which would indicate a larger rate of decay, a faster rate of decay. But this is one that will always work. We can always find that. So if our system is, so it turns out for a linear system, I can always find an alpha that proves that I have an exponential rate of decay. And in fact, this is a value of alpha that can do that. So again, there may be actually a larger or alpha giving a faster rate of decay, but this is always one we can always find. So for quadratic decay, so remember the quadratic inequality was this: v dot x of t must be less than or equal to minus alpha times the 2 norm of x, not v of x, but the 2 norm of x. So, so that's the definition for quadratic stability. So v dot of x is equal to minus x transpose qx. And this I can always prove is less than or equal to minus the smallest singular value of q times x transpose x. So it doesn't involve p at all. So we actually have a simpler inequality here. But this shows a quadratic rate of decay. So again, for any linear system, I can always find that my system is quadratically stable. So it's not only, if it's asymptotically stable, it's exponentially stable, and it's quadratically stable. Any linear system. Now, if I have this equation, how do I compute A transpose P plus PA plus Q? Well, again, this is a linear equation in P and in Q. So if I'm given a P, I can find a Q. Now, it turns out that if I find a P, if I pick a positive definite P and I solve for Q from this equation, there's no guarantee that Q is going to be positive definite. There's no guarantee because it depends upon A. However, if I choose a Q that's positive definite, I can always find a P that satisfies this linear equation if my system is stable. But the system being stable is not the only case in which I can have a solution to this equation. I can get a solution to this equation even if my system is not stable. In fact, so that can happen. And in fact, that's what does happen if you have an unstable A. That means you'll pick a positive definite Q, but the P you get will not be positive definite, which means you don't have a Lyapunov function, right? So that's what happens. But I can still solve this. Notice that in that case, the solution is not that infinite integral, it's something else. But again, because this is a linear matrix equation, I can actually solve for it from a number of ways. So in MATLAB, we can use the command lyop. And lyop actually wants to do something like, instead of A transpose P plus PA, it wants to do AP plus PA transpose. It wants to use the transpose version. So that's why when we want the solution to this equation, we have to use the transpose in computing the Lyapunov function. So in MATLAB, we can do that. Or we could also use the symbolic math toolbox, but that's more complicated because we actually need to solve for, we let P be a symbolic matrix. We pick a Q, multiplying it out, I'm going to get a set of equations and unknowns in the coefficients of P, and then I need to solve those. And so there's definitely more work involved. This is definitely the simple way. So by way of summary, x dot is equal to ax. Here is my quadratic Lyapunov candidate function. I get this derivative along the system trajectory, which leads to this Lyapunov equation. So this Lyapunov equation, if P is positive definite and Q is positive definite, then A must be Hurwitz. Alternately, if A is Hurwitz and Q is positive definite, then P is positive definite, and in fact, P can be expressed this way. So in terms of summary of quadratic Lyapunov stability for linear time invariant systems, I have the continuous time and the discrete time, and they're very similar to one another. So here are the results that I get in both of these cases. They're very similar to one another. So by the same approach we use for continuous time, we have a similar approach for discrete time. So we're actually able to handle. So as I mentioned to you, in controls, one of the things I like about controls is that the further you go, instead of becoming more narrow and focused, we actually become more broad. We're able to handle a broader class of systems. So we can not only handle continuous time, but we can handle discrete time systems. So in continuous time systems, we have these linear matrix inequalities. So P positive definite, A transpose P plus PA must be negative definite. So this will prove the stability of A. Alternately, we can have what's called the dual form, where I would have a Q positive definite, and Q and A must satisfy this inequality. So this would prove the stability actually of A transpose. But the spectrum of A, that is the eigenvalues of A, are equal to the eigenvalues of A transpose. So you can actually go through and show that, and so that's what we have. In discrete time, we have a similar set of inequalities. We have the A transpose on this side for the P, and A transpose on that side for the Q. And again, since the spectrum, the eigenvalues of A are equal to the eigenvalues, or the spectrum of A is equal to the spectrum of A transpose, the spectral radius of A is equal to the spectral radius of A transpose. So we have these linear matrix inequality forms for both continuous time and discrete time. So we notice that they're fairly straightforward. Notice that this is actually a linear matrix inequality both in P and in A, whereas this is a linear matrix inequality in P, but not in A. This is a quadratic in A. So how do we compute solutions of this guy? Well, given A and Q, how do we compute solutions? Well, there's the brute force method. Again, let P be symbolic. So if I pick Q and I have A, I can solve for P from this equation. That will give me some equations and unknowns, and I solve them. I can use the infinite summation formula. In discrete time, I can use the d-Lyop. That should say d-Lyop. I can also solve it using Kronecker products. I'm not going to go into that here. So I have means of solving these equations.